Good. So I hope you can hear better now. Now, we are going to extend the filtration to negative degrees. So we make it 0 here. And then k minus 1 is actually the same as k. Okay. So it's good to introduce negative degrees so that you don't have to worry about where the beginning is, you know. Okay, so yeah, so we extend Kp to all p in Z by say setting Kp equals K where P negative. Okay. You know, then for each P, okay? So K, P plus 1 is contained in Kp. So you have a map. So there is the inclusion map. And then, so you can sum this up over all P. And it's actually an inclusion map. Yeah, so I'll put it here, I0. Yeah, so this is why I want negative P's, you know, so that like when P is minus 1, you know, like you can still map into K0. Yeah, anyway, so, and then this is an inclusion. So you can take the quotient. Oh yeah, let's do it over here. Already you have an inclusion map. And so you can take the quotient Kp over Kp plus 1. Yeah, so you have an exact sequence. And you can sum it up over all P. Okay. Yeah. Okay, so now you have a short exact sequence of differential complexes, okay? Because big D takes each Kp into Kp. And this we call C, okay? And this is the same thing, C. And then this we call B, okay? So this is a short exact sequence of complexes. And we know that it induces a long exact sequence that we can arrange as a triangle, okay? So this short exact sequence is of differential complexes induces a long exact sequence in cohomology that I can arrange as a triangle okay. And this is an exact couple. Oh, so I'm writing HC instead of H big D of C, all right? So this is just a simplified notation. So notation, yeah, H of C, it's H big D of C. Okay. So this is an exact couple, and we call it our A1. And and E1. Okay, and so the maps are I1, J1, K1. Okay. Now this is actually, this K, right, is actually the, connecting homomorphism. What did we call it? Well, I think we called it D star before. This was like, well, let's just call it K. And then by taking derived couples, you get an infinite sequence of exact exact couples. Okay, so taking derived couples gives an infinite sequence of exact couples. And when you take derived couples, right, each time this ER is the cohomology of the previous ER, and it is with respect to dr minus 1. So, so you get an infinite sequence of differential groups. Each one is the cohomology of its predecessor, and that's a spectral sequence. So this gives the spectral sequence of the filter complex of KD so it's just ER, R going from 1 to infinity. And the question now is, what does this spectral sequence compute? Okay. Yeah. So what I'm going to show is that it actually computes not quite H big D of K, but there is a filtration on the cohomology HD of K. And what this spectral sequence gives you is the associated gradient complex of HD of K with respect to that filtration, okay? So let me tell you the filtration on HD of K. There is a filtration, or the induced filtration on HD of K. Yeah. Okay, so A1, where's A1? A1, right. Yeah. Okay. So A1 is the cohomology of C, and C is this direct sum. Yeah. Okay, so A1 is the cohomology of C, and C is the direct sum of KP. And this is the direct sum of H of KP. Okay. And so you can write it out. It's the direct sum of, okay, the terms are H of K. Now, you actually have H of K minus 1, but, you know, that's the same as H of K, right? Okay. H of K is H of K0. And then, you know, H of K1, well, K1 is included in K0. So that inclusion induces a map in cohomology, right? That we call I, right? This inclusion, I0, okay, gives you a map in cohomology we call I. And similarly, H of K2 maps to H of K1 by I. So it goes on forever in both directions. And A1 is the direct sum of all of these terms. Now, A2, by the definition of an exact couple, A2 is I of A1. So you just apply I to all the terms. But, you know, here, yeah, there's this map. This map I is equality, right? So when you apply I to H of K, you still get H of K. so let's see. So here you, yeah, I apply I to everything, but I of HK is the same as HK. And then, so this is H of K0, IH of K0, okay? And then IH of K1, IHK2, IHK3, okay? And then out here, I actually, it's gonna be all, you know, HK. A2 is the direct sum of all of these terms. Okay? And the I's are not inclusions, right? Because they are maps in homology induced by an inclusion, you know, so they're not inclusions in general. However, you notice that, you know, I of HK1, that's the image of H of K1. So it is contained in H of K0, okay? So this map here, I of HK1, when it maps into H of K, it's actually an inclusion. This first map is an inclusion. The other maps may not be inclusions. Now, okay, now, but now let's look at if you go to A3, you know, then you apply I again to all of these terms, right? So A3 is IA2 by definition, okay? Okay, so where is IHK2? You see, yeah, so now let me see. So, okay. Okay, when you apply I to K2, now you'll have II HK2, okay? That is gonna map to II HK1. And the new map is still called I, right? This because we showed last time that all the I's, all the IRs are actually just I restricted to a smaller group. Okay, but this one, you see, this is an inclusion. This I is an inclusion. So it doesn't change this group, right? You just put that group inside, okay? So this is actually the same as I H of K1. And sorry, yeah. I actually want to see where II is, so just a minute. I'm gonna do this, okay? So I2 is I, and it takes, yeah, this is I2, right? It's just a restriction of I. It takes IHK2 to IHK1, You take IHK2 to IHK1. Yeah, okay. And so, so that means IIHK2, okay? So that's the image of I2. That should be contained in I of HK1. So this is, we can write this as I square HK2. If you apply I twice, then it becomes a subgroup. And then if you look at I3, okay, that's also I. That's going to go from IIHK2 to IIHK1. But because this first I is an inclusion, it doesn't do anything. So this is the same as IH. Oh, no, sorry. And now I want to look at K3, okay, into K2. Yeah. And right. And so you see that IHK3, okay, that's the image of I3. So it should be contained in I2 HK2. Okay. And this is I3 HK3. Okay. What I'm saying is that you actually get a sequence of subgroups. Okay. So you have H of K, and it contains as a subgroup IHK1, and then IHK1 contains as a subgroup I square HK2. I square HK2 contains as a subgroup I cube HK3. Okay? So you get a sequence of subgroups of HK. Okay? Thus, thus. We get a sequence of subgroups starting with H of K contains I H of K1, and that contains I square H of K2. That contains I cube H of K3, and so on. So what do you call a sequence of subgroups? It's a sequence of subgroups. It's a filtration. Okay? Okay, so this is a filtration on H of K. So this sequence of subgroups, it's called the induced filtration on H of K. Induced filtration on H of K. So it is induced by the filtration the AP on K. Okay? Yeah. K is a filter complex. It comes with this filtration KP. And now we see that there is naturally a filtration on the cohomology. Yeah. And so this spectral sequence that we get, from all the derived couples, it eventually stabilizes, So eventually, and it gives us, well, not under suitable condition, like if the filtration has finite length, and then that ER for R large is then the associated Grady complex of HK under this filtration. Okay, so let me state the theorem. And this is only for filtration of finite length. So theorem. Okay, now to make it simple, we'll just assume that the filtration has length 3. Okay, okay, we are working in the category of abelian groups. So these are all abelian groups. So suppose the differential complex KD has a filtration of length 3. So that means you terminate after A3. Okay, then the conclusion is that starting with A4, everything stays the same. Okay, so the A's stabilizes, and so that you can call A infinity. They're all the same, and the map I also stabilizes. So I4 is equal to I5 is equal to I6, and so on. And all of these are inclusions. And then the E's also stabilizes. And so you can call that E infinity. And E infinity is the associated Grady complex of H of K. So with respect to the induced filtration. Now, in the category of vector spaces, if you have finite length, then the associated Grady complex is the same as, this HK itself, So if you're working with vector spaces, then the spectral sequence actually computes HK. Okay? Yeah. So as I said, a spectral sequence is like a book with many pages, and so the first page is A1, the second page is A2, and so on. And when you turn the pages, each page is the cohomology of the previous page. And so what the theorem says is that if you start with the finite filtration of length 3, then, after you turn a few pages, when you get to page 4, you find the cohomology of the double complex. Yeah. And we'll do specific examples, to show you that it actually computes cohomology. But let's try to prove this theorem, okay? When we have length 3, so now let me see. All right, okay. So A1 is the direct sum of these terms here. So we have length 3, and that means it's going to terminate here. Okay, so this is A1. And then now A2 is when you apply I to everything. So I of HK1 is going to be a subgroup here. I of HK2 is a subgroup here. I of HK3 is a subgroup of that. And there is a map I2 here, but it's still I. And then this is followed by 0, 0 is a subgroup of that. And then here you have I of HK0, because you have to apply I to everything. But I of HK0, just a minute. This is HK0, HK1 is here. So I of HK0 is here. But this I is equality, so this is actually equality. And from here on, it's all equalities, right? And so you have a map I here. I of HK1, well, this is actually an inclusion. I of HK1 is contained in H of K. This is H of K. Yeah. Okay. Okay, now let me see. I of HK1 is in here. um, uh, uh, oh, so what is the difference between this row and this row? Now, yeah, so I guess we just know that this is an inclusion, right? Yeah. Oh, well, yeah. We already know that this is an inclusion, but if we didn't, you see, this map is this inclusion followed by equality. So yeah, this is definitely an inclusion, okay? So the second row differs from the first row in that one of the maps has turned into an inclusion. Okay? So A2 is the direct sum of all of these terms. And yeah, so now let's look at A3. Okay. Okay. I'm going to write directly below. Now, A3 is obtained from A2 by applying I to everything. Okay? When you apply I to H of K, it's still H of K. And then you apply I to this, but since this I is an inclusion, it doesn't change the group. So it still get IH, IHK. Yeah, but I'm going to write IHK here. IHK, okay, because you have mapped it in here, right? So IHK is contained in HOK, and then I square HOK is contained in here. Probably I should write it on the same blackboard. IHK1 is contained in here, and then IIHK2 is contained in there, and IIH of K3 is contained in there, and that's followed by 0. And you have these maps I, okay? Okay. Okay. Now, what can you say about this map I from the commutative diagram? This map. Can you say that it's an inclusion? Remember, you have a commutative diagram here. So this map, okay, followed by this, it goes in here, right? It's the same as this going this way, okay? So going this way, you have an inclusion followed by an inclusion. So this going this way, it has to be an inclusion also. So this map is an inclusion by the commutativity of the diagram. And yeah, this is case H of K. Okay? And so this, it goes to H of K. So now you have two inclusion maps. Okay. Yeah. So by the commutativity of the diagram, the map I from IHK2 to IHK1 is an inclusion. Okay. And now if you go one step further, so this is going to be under I, it's going to be a subgroup of this, right? And then this is going to be a subgroup of this. So, but I is an inclusion, so it doesn't change anything. And this map here, again, by the commutativity of the diagram, it's also an inclusion. Okay. So in I3, all the I's become inclusions. In A3, all the I's become inclusions. All the maps I become inclusions. All right? So here is in A3, right? And this map is, just a minute. Oh, yeah, I guess you're right. Now this is the next one, A4. You are right, A4. So this row is A4. So in A4, then you have H of K, and then IHK1, that's an inclusion, and then IIHK2, inclusion, IIIHK3 as an inclusion. Okay, and here it goes on forever in the negative p's, and they're all the same, right? Yeah, and now once they become inclusions, if you apply I again, it doesn't change anything because an inclusion does not change the group. Okay, and so yeah, so A5, since inclusion does not change the group, so this shows that A5 is going to be the same as A4, okay? Because if you apply I to everything, now it's inclusion, so nothing changes. Okay, so A5 A5 will be equal to A4. A5 is I of A4, and that will be the same as A4. Okay, and then A6 will be the same as A5 and is the same as A4. Okay, so all the A's will stabilize. And then all the I's, they're just restrictions of inclusions. So I5 is I4 restricted to A5, and that's an inclusion. So nothing changes. So I4 is the same as I5, is the same as I6. Okay? And they are all inclusions. And, so you have this exact couple. And and so by exactness, the image of K4 is the kernel of I4, but the kernel of I4 is 0, right? Because I4 is an inclusion. And so that says K4 is the 0 map. And what is D4? And this implies that D4 is defined to be J composed with K. So that's the 0 map. The differential is a 0 map, therefore E5, which is by definition the cohomology of E4 with the differential D4, because the differential is a 0 map, the cohomology doesn't change. Huh? And then similarly, the same argument proves that E6 is E5. So E4 is E5 equals E6, and so on. Okay? So it stabilizes. Yeah. So once you turn the book 4 times, then you get the answer E infinity. Okay? Let's take a break now, and then after the break, I will show that E infinity is the associated gradient complex of the cohomology HD of K. Okay, so let's get started again. Now, A4 we know that it's the direct sum. Oh, excuse me. I need the microphone. Okay. All right, so we know that A4 is the direct sum of the terms in this sequence. You have h of k, okay, that's h of k0, and then it contains IHK1, contains I square HK2, which contains I cube HK3. And then after that is 0. And this goes on forever, right? HK0 is H of K. Okay. Now, so this group is what we call F1. This is F2. This is F3. Okay. And this is F0. Yeah. And this map is I. It's I4. So A4 is the direct sum of F sub P, where P can be negative also. But the thing is that when it's negative, it's just the same as H of K. So P is less than or equal to 3. Okay. That's A4. And then I4 goes from A4 to A4. So I4 is the same as I. It goes from A4 to A4. Okay. Is an inclusion, but is it the identity map? It goes from A4 to A4, and it's an inclusion. Does that mean that it's the identity map? Well, like you can have an inclusion that's not the identity map, right? Like you can include Z inside Z by sending, say, X to 2X. No, just a minute. Oh, no, it's not quite like that. No, because we don't actually change the element. Now this I, the original I, it came from I0 in C, right? I0 going from C to C, and C was the direct sum of KP plus 1 to KP. And I0 actually sends Kp plus 1 to Kp as an inclusion, right? But so it's not the identity map. It's an inclusion, but it's not the identity map. Okay? Because you don't send Kp to Kp, you send Kp plus 1 to Kp. Okay? And I is induced from this. So it actually, you know, this K1, yeah, you should write this as F sub Kp plus 1. It's the same thing. And I, it actually sends F sub Kp plus 1 to F sub P. Because it's induced from this. So Kp plus 1 goes to, yeah, so K2 goes to K1, you know, and when you write it out as a direct sum, yeah, so H2 goes to H1, right? H2 goes to H1, and then you take the direct sum. Yeah, so this map is not the identity, it's not the identity map, okay? Yeah, yeah, it comes from sending F2 to F1, F3 to F2, and so on. It's an inclusion, but not the identity. And therefore, its quotient is not 0. Okay? So, so so the quotient is Fp over Fp plus 1. Okay, so you have this exact sequence. This is your I. And it's also I4. And then if you sum it up, over all p less than or equal to 3, you get this. Okay, so this is exact. And this is A4. This is A4. And so right, and in the exact couple, so you have A4, A4, J4, E4, but this map is 0. So E4 is the quotient. Okay, yeah, that means, yeah, so E4 is the quotient of this A4 under this map, I4. Therefore, this is E4. Now, when P is -1, okay, so f of -1, that's the same as f of 0, right? F of -1 is the same as f of 0. Yeah. For negative p's, these two groups are the same. And so this you can actually just sum from p equal to 0 to 3. And you see that this is precisely, the associated Grady complex of this filtration. This is the induced filtration on H of K, right? Because yeah. So in general, you see that f of p is I to the p of H of K of p. That was the definition of the induced filtration. Okay? So thus, yeah, so this is the associated Grady complex of H of D with respect to the induced filtration. So here, that's since f minus 1 equals f0. No, f0 is f minus 1 equals f minus 2. Yeah. Okay, so you don't need the negative terms. You go from 0 to 3, and that's precisely the associated Grady complex of the cohomology. Okay? And so we have proven this theorem. We have proven our theorem. For a filtration of length 3. But you can see that the same argument will work for any filtration of finite length. So if you change 3 to L, then here you'll terminate at KL. And then the conclusion would be that starting with L plus 1, everything will stabilize. Okay? Instead of 4, put in L plus 1. L plus 3. And then okay, and E infinity will be the associated Grady complex of the cohomology of K. Yeah, all right. Now, usually, spectral sequences are considered to be complicated. And if you try to read about it, in most books, it's just, really involved. But yeah, you see, like, using this presentation, it's not that complicated, okay? So you can compute the cohomology of a filter complex with a spectral sequence. Okay, now there's one problem here. This is actually a very severe restriction that you have a filtration of finite length. Yeah, so next time we'll talk about a similar theorem, but for filtration of infinite length. Okay, and you'll get the same conclusion, provided that you take into account the degree, and if in each degree you have a filtration of finite length, then you still have the same conclusion. Now having a finite filtration in each degree doesn't mean that you have a finite filtration on the complex, because the length could increase with the degree, right? Yeah. But yeah, okay. So we'll deal with that situation next time. Okay. Yeah.